Hello, I'm Rich Eisenberg, the Editor-in-Chief of Inorganic Chemistry. As part of our 50th anniversary year, we are having interviews with leaders in the field of inorganic chemistry and inorganic chemically related science. And it's a particular pleasure for me today to interview Professor Richard Holm of Harvard University. Dick and I go back a long way. We're very good friends, and it's a real honor to have him here. He's one of the leaders in our field, having won ACS awards, member of the National Academy and the National Academy of Sciences Award in Chemical Sciences. In any case, Dick, welcome.
Thank you.
And it's great to have you here. Even though I know it, since we go back about 40 years, tell us a little bit about the early Holm years and how your education and training and early research led you into the chemistry that you did for your career.
Well, I got into chemistry actually in a sort of default way because I was brought up in a very small town off in the coast of Massachusetts. It had, shall we say, limited educational offerings at that time. And I don't think the word chemistry ever crossed my mind when I was in my teenage years. My interests were really in things like English literature and education, religion, and baseball. When I went to university, I intended to conduct my career such that I would be a high school English teacher or perhaps a professor of English. But after a couple of years, I decided that these rather amorphous liberal arts subjects were perhaps not best for me. And I was looking for something more definite, more quantitative to grapple with, and I discovered chemistry when I was in my second year in college and found that it was really quite interesting. It was my best alternative, and so by the time I got to be a junior, I decided that I will take it up and give it a try for a career, and it was a very fortunate choice. I also had, as often happens to college students, a professor who took interest in me for some reason I'll never know, and he helped me, move me in that direction. So that's how I got into it. I wasn't one of these kids with the chemistry set at the age of 10, I'm afraid. But I did evolve into the subject along that path.
Right, and then you went to MIT for graduate study and worked with Al Cotton.
I did. I was one of the early people in his group. He was must have been 25 or 26 when I first encountered him, but it was very clear that this was a rising star, and it was attractive to young people 20 years old to affiliate with somebody who was going to go a long way, and that was one of the reasons that drew me to Al, in addition to the fountain of ideas he had about everything in the inorganic field.
What were the first things that you worked on independently, and where did you start your early career?
Well, after I got through with graduate school, this instructor's position at Harvard opened up, and I applied for it and I got it, and I decided then I would work on several different things. One of them was the search for triplet ground states and planar nickel complexes. That's an old question, but one that was quite alluring at the time because it represented a prediction of crystal field theory that, however, was not realized until about 40 years later, and I didn't in my original work. And then, as you know, Rich, shifted over to this very interesting subject of metal dithiolines and paramagnetic NMR and other things of that sort that I began with in that position at Harvard.
So the key themes that ran from your early years throughout your research, you would say would involve redox-active materials, redox-active compounds, ligands.
Yeah, I mean, I was interested in all of those things. I certainly was interested in inorganic synthesis, and I still am today. In fact, I think that's probably the principal occupation of my lab for the last 20 years, is making new molecules that have relationships to certain biological questions. But all of those things are interesting, and back in the 1960s, it was very hard not to be interested in everything because the field was wide open. Activity was rather low, the number of people working in it not large, and so it wasn't hard to find good problems. And I was fortunate enough to find a couple, one of which you were involved in yourself in that period of time. the metal dithiolines. But there were other things that also interested me. I always regarded my function in the subject as one of pure inquiry. And so that means you have to identify good problems and take them to some kind of logical conclusion. And I don't know whether we've ever done that in toto, but we certainly have endeavored to do so. At Harvard, I had three very good friends who worked with me as a team: Gus Mackey, Norman Eldstein, and Alan Davison, and we worked very hard, and we were quite aware of what was going on at Columbia and with the Schrautzer lab at Emeryville in California. But competition, you could put it that way. Maybe you guys viewed it that way. We were simply trying to do our work. Mm-hmm. But anyway, the result was that there are three groups of people working on an interesting and new subject, and I think that helped move it along at a faster rate than if it had been just one research group tackling the subject.
One of the areas that I think you're particularly noted for are iron-sulfur clusters, and tell us how you got into them and the importance of those clusters in biology.
Well, there's a little bit of background here. Along about 1968 or 69, I was looking for something different to do. Despite the freshness of subjects that I had worked on, I was nonetheless getting a little bit, I wouldn't say bored, but maybe fatigued with these subjects, and so I wanted to do something else. And I met a biochemist who told me that given my interests, I should attend a meeting called Metal Ions in Biology. It's a Gordon conference. It was held in New Hampshire at that time, and I went there. In the 1968 meeting, there was a talk given by Helmut Beinert, who was a noted biophysicist who's died recently. But he gave a nearly hour-long talk on strange EPR signals that were elicited from mitochondrial enzymes when they were reduced. And this is where this famous G equal 1.94 spectrum was first mentioned to me. It had been known for a couple of years before then. But anyway, here were molecules, biological molecules that were giving spectroscopic signals of a sort that had not been seen before, were not understood. And I sat there and thought there must be structures associated with them, and what are these structures? I didn't do anything about that for several years, but then I began in the early 1970s to work on this subject, and everything we did for a while was wrong, and then ultimately, however, we did find that combinations of metal thiolates and sulfur and iron salts would generate interesting structures. And so that's how it began. It began because I was fortunate enough to be at a meeting where somebody presented a problem, although he didn't present it in quite the way that the inorganic chemist would pursue it.
Well, it speaks well to go to meetings, even if you're not necessarily presenting at those meetings, but to learn information about it. In terms of the research that you've done, would you say that there were any, now this sounds funny for you, but Eureka moments when you suddenly realized that you had either cracked a problem wide open or reached a fuller level of understanding than you had before?
Well, it's sort of like asking whether the goddess Fortuna has ever visited my lab. Yeah. And I'm not quite sure that that it has happened, but I've had a couple of moments where I thought we did something that was exceptionally useful, and one of them was recognizing the electron transfer capabilities of metal dithiolanes, which was our first contribution to that subject, you may remember, back about 1962. So that was sort of a eureka moment because it led to a lot of very interesting work by not only ourselves, but the group you were in and others as well. And it did represent the start, I think, of the development of metal dithiolane chemistry. I think the synthesis of the three basic types of iron-sulfur clusters had the value of showing that there was a subject called biomimetic inorganic chemistry, and if properly executed, could contribute not only to inorganic chemistry per se, but to biological problems as well. And it wasn't so focused that I'd want to say that I jumped up and said Eureka, but I did think that at least on a collective basis, this was a very positive contribution. And later on, there have been other things that I think have felt rather very good about, including the emergence of metal dithiolane chemistry in biology, starting, for me at least, around 2000, and we've worked hard on that. That isn't a eureka moment, but it's a very satisfying one to be able to come back to something that you had a hand in starting originally and see how it can be used in a completely different context.
Were those the oxotransferases
Yes,
with molybdenum and tungsten?
Right.
Yeah, okay. And what are your thoughts now about the iron molybdenum cluster, and how close are we to having a really good viable model of how that works?
Well, there is no problem in chemistry that interests me more than the biological and chemical synthesis of the catalytic center of nitrogenase. And it is very interesting to realize that we may understand, not in an atomic level detail, but in one step up, the pathway to the synthesis of that molecule before we actually make it chemically in the lab. That could very well happen. But the elemental steps by which this rather complicated molecule is built, to me, must be the same in the chemistry lab as in the cell. And I'm hoping that before time runs out for me, I'll be able to push further toward that objective. But to be able to synthesize a molecule which is the catalyst for one of the most important reactions on this planet is an undeniably romantic goal, and possibly an attainable one. At least I hope so.
How have you found the crystallographic results for the nitrogenase? I know that at one point there was this cluster without an atom in the center, and then suddenly it was revised to have an atom in the center, whether that takes people who are working on models for that and causes them great angst.
Well, it certainly makes the problem more complicated, but you know, there would not be the progress that we have made in the chemistry and biochemistry of nitrogenase without the structural results from Caltech and some also from Britain. And the fact that in 2002 it was discovered that the cofactor cluster had an unknown atom X inside it complicates any conception one might have about how to synthesize that molecule chemically. But at the same time, it raises a challenge as to how to do it, because so far as I know, nobody has figured out the problem of introducing atoms interstitially in any cluster on purpose. And that is what you need to do here. So that produces a difficulty, but yet it also produces a challenge, as difficulties tend to do in science.
Okay. We may have touched on this before when I asked you about Eureka moments, but I'm going to ask you in a slightly different way or wording. Just your proudest accomplishments in chemistry.
I think the research that I've liked the best, I've already mentioned to you, the early diethylene work, our contributions to paramagnetic NMR, metal clusters in biology. These are things that I think have been most helpful. But another accomplishment, or I don't know whether I want to call it an accomplishment, but another pleasing fact is the progression of people that have come through my laboratory. Whether they've benefited from it, you'd have to ask them. But it has been an enormous pleasure to have dealt with so many fine people over the years.
Have you
How many
mentored
PhD students?
PhD, and
Yeah,
how many
I don't-
postdoctorals do you have?
Yeah, I don't keep lists, but I would say probably about 60 PhD students and well over 100 postdoctorals.
And I know that they're in positions of eminence around the world in terms.
Some have done very well,
Yeah.
very well indeed. You know, Rich, there's much to be said, even when you're a young man, for working with people who are younger than yourself. And that's one lesson I have learned, and I continue to enjoy it today.
Okay. Now, I know that your papers have always been paragons of scholarship and innovative research. What would you tell young investigators today with regard to their communicating their science?
Well, it's never been easier to communicate your science than it is today because of the internet and all of the advances that we have. I would say to young investigators today, in your papers, get to the point. Drop the hype, get to the point. Make your papers interesting but concise, and don't publish too many of them. We're awash in information, and I don't know about you or other people, but it's a virtually impossible task, even with electronic retrieval of information, to keep up with it. And I would hope that we could have some discipline in terms of producing as much, but reporting it in a smaller number of articles. There's some entropy here that's not useful, I think, in the publishing game. So that's what I would suggest to people. On the other side of the coin, we both know that advancement in academia is often related to the volume of productivity, and that's a factor I wish would not be as important as it is. So I would say be economical in what you publish, and be clear, and be relatively short.
How do you feel that the funding picture influences how people today will write their papers and frame their research versus when you started?
Well, when I started, there was really no issue here at all. I mean, the NSF was in the business of supporting pure research, pure inquiry. The NIH was very generous, and even though being founded as a health-related organization, was very, very generous in supporting pure chemistry, particularly pure organic chemistry. Today, things are very different. Funds are much harder to get. The situation is more competitive. And today, people are, to some extent, following the research dollar, as they have to stay alive in this climate. I don't object to that particularly. I just don't want these agencies to lose track that the greatest advances are often made by people who are simply interested in, as I said earlier, pure inquiry. You can't give somebody a blank check because they say, I'm interested in, exploring some area to find out what's there. But you can be tolerant of good people asking broad questions.
I think that's a great point. The question of how you choose your research area, and part of it is an applications focus, but part of it has to be the fundamental science, and that's what will make a great problem.
Well, that's what I believe in, and that's how I've attempted to conduct my career. And but one may also say that I've had it somewhat easy because I've not run up against these forces that require you to do something practical and pragmatic in order that your funding be continued. Funding agencies have been very generous to me, and I've always been able to raise money on the basis of problems that do not have any obvious practical import. That's not so easy today, and that is it's a climate in which I think at least some quotient of our younger investigators feel where they get ahead faster if they do something which is going to have a payoff. Most often in terms of synthesizing materials which have certain desirable performance characteristics, magnetism, conductivity, you name it, things of that sort. Again, there's nothing wrong with that so long as if you do it in a university, you do it because it's a matter of basic fundamental work, not because you're trying to make a product.
Part of what you've just said also relates, though, to how chemistry has changed. And when you started out, just the mere fact of making molecules, doing structures, looking at their spectroscopy was a viable way to go. It was good. Things are different today. Can you prognosticate into the future? How do you see our field moving?
If you mean by our field inorganic chemistry, I would say it's it's sort of like the galaxy. It's expanding rapidly in every direction. And that is one of the problems we have today because it's a hard field to define. When you speak to people and they say, well, I want to make an appointment in organic chemistry, what is your advice? That's very hard for me to answer because there are so many different areas. So it's inevitable that this field, which deals with all of the elements in the periodic table, is moving in all kinds of different directions. And some of them are in these very practical, pragmatic directions I mentioned a moment ago. And we still have a coterie of investigators who are working on things because they're interesting and because they can justify their interest. But research has changed a great deal, and no small part of that is the availability of the research dollar, which more and more comes into things that are going to be of tangible help to people.
Yeah. Instrumentation has also changed. From my own personal experience, doing a crystal structure, which we did a long time ago, It was a 3-month exercise. Today you can do it in 6 hours. NMR, doing a 2D NMR, unheard of then.
Well, Rich, when you were doing things, I remember your work in those days, and a couple of crystal structures would be a PhD thesis.
They were.
Just about, or maybe they were, I don't know. But
yeah.
It's desirable more than anything else. The advances that have been made in X-ray crystallography are stunning. In NMR are stunning. And so it goes for other techniques as well. Theory, absolutely. Now that's all of that's an upside, and a powerful upside. There's a downside, and the downside relates to what the students know and understand. When they, for example, do a crystal structure, I doubt very much if many of them have ever studied the physics of crystallography or know anything about scattering theory or Fourier transforms or things that you know about, because you learned the subject in a different era. But when they get the output from the structure analysis, they know what it means and they know what to do with it. Perhaps that's enough. Likewise for NMR, I don't know if anybody in my lab would know what a free induction decay curve is or would know some of these fancy multidimensional methods, but if you confront them with the results of those methods, they will be able to understand them. Is that good enough? I guess it depends on your point of view. To me, it's not quite good enough, but nonetheless, the students can progress well and interpret things correctly. So advancement in chemistry is just fantastic in terms of instrumental development, and it's not going to stop. You'll have your next crystal structure in 2 hours, probably.
That's right.
You know?
That's right.
And done on the tabletop with a small instrument.
But I think with all these new methods and techniques, we ask our students now and expect our faculty now to cover problems of greater scope than they may have done in the past.
We do, and the development of instrumentation has had another interesting consequence, and that is it's kind of like a leveling effect. Most good research universities have about the same equipment unless it's very specialized, and that means that investigators at places that used to be somewhat disadvantaged with regard to that aspect aren't anymore, and so you can be practically anywhere and take on these tough problems that require instruments because you have them. And that to me is a very important thing. People sometimes overlook that, but I have nothing but admiration for the people who have developed these instruments and these computer programs. Theory is another area. Now we see so much use of density functional theory, probably by those who do not have a deep fundamental understanding of it, but know what it means when they do the calculations.
Yeah. I want to turn to inorganic chemistry with capital I, capital C, meaning the journal.
Yes.
Yeah. You started your independent career when inorganic chemistry started. You published in the first volume. I believe that you've published in every volume since then. Tell us a little bit about your experiences with the early inorganic chemistry, and then we'll move to the later inorganic chemistry.
Well, the early inorganic chemistry was really a source of considerable pleasure to me. Before the first issue came out in 1962, there was this rumor that the ACS had accepted the idea of creating a journal like this. The editor was selected and the first issues came out, and I remember thinking to myself, I was like, 26 years old or something at the time. I remember thinking to myself, well, now I don't have to worry about where I'm going to publish things. I can publish them in this journal. Well, the journal at that time wasn't the equal of JPCL or many other journals because it was so new, and its clientele had not been established, and it didn't have in its early years a steady editorial population, you might say. There was some changes that went on in there. But the journal began to grow, and it is the flagship of our subject. It's the first journal I want to look at. When I can still pick one up and put it in my hands, I guess that's going to end shortly. But no, to me, it's the most important scientific journal that I deal with, and it's grown very well. And one can think of the 30-year editorship of Fred Hawthorne, and how the journal progressed from immaturity to the primary inorganic chemistry journal in the world, and now you've of course taken it even further. So it's a source of great pride to me to have published, if I have really, in every issue, but just to have been affiliated with that journal in one way or another is something that I value.
I'd like to ask you about the challenges and opportunities you see with regard to the journal as we go forward in time. Our field is, as you said, like the galaxy, it's expanding, and there are efforts into the biological sciences, there are efforts into material sciences, there are applications, catalysis. So people working in this field wind up, or in inorganically related subjects, wind up talking to other audiences. And this remains then one of the challenges for us and opportunities. What special qualities would a journal in inorganic chemistry have for all of those researchers?
Well, I'm delighted I'm not the editor, because you're really asking, what criteria should I apply for a journal, for a paper to be considered appropriate to the Journal of Inorganic Chemistry, and that's very hard to decide. I think what I would be least warm to, if I were you, would be a lot of computational papers which don't carry any experimental information in them. And I wouldn't certainly want papers with a large organic content to be in them either. But beyond that, it's very hard to pick and choose. Very hard. And you can't restrict it, for example, to molecular chemistry, because that would be a serious error today. So there isn't any formula. I don't know how you do it. I'd like to know, but it's a very difficult choice to decide what's appropriate and what isn't for the journal.
I've thought that being able to have, let's say, papers that deal with methane monooxygenase and CH bond activation by iridium or rhodium compounds, that there's a commonality with regard to that. Your own experiences with, let's say, nickel CO dehydrogenase and rhodium catalysis and things of that type would be a good unifying.
Well, yes. I mean, you could say that. Well, if I'm interested in CH activation in my journal, then I should be interested in methane monooxygenase in my journal, because after all, there are vast differences in the chemical system, but the issues are, fundamental reactivity issues are similar. I think what may save guys like you, Rich, is that the authors will be self-selective. That is, authors will want their papers in a certain journal and feel that being in another one is not as useful. So it may be that self-selectivity will help you. I don't even know whether this is an issue with Inorgem today or not. I suspect not.
We also, we're a global community now, more than we ever were. And most of the authorship comes from outside the United States. This is true for ACS publications in general, and we serve to pull together a truly global village in this.
Do you have more papers from outside the U.S. in Inorgem today than from within?
Yeah. And that's true, I think, for all of the ACS publications on average, that foreign authorship exceeds domestic authorship.
Well, I guess that's the way, that's the market.
The way science is going.
Yes, exactly right.
That's actually an interesting, again, another, I think, very positive development in the world.
Well, there's plenty of competition. I mean, there's this whole swath of new journals in Europe, and there's an Asian Journal of Chemistry now, and some other things in India. Mm-hmm. So there's plenty of competition out there, and there's plenty of places for people to publish, including the papers that you don't want. So I think you're in pretty good shape. It doesn't bother me that it's more than 50% outside the U.S. It may be an American journal, but science is not an American province.
Well, we've been delighted to have this interview with you and get a chance to talk, and I know that you will keep doing research until you finally crack the nut of the iron molybdenum cofactor, which I hope you do shortly.
There's a saying, Rich, which I can repeat to you because I've said it to at least one audience. I will keep working on this until I succeed or until the money runs out. And I'm not sure which will come first.
I hope success.
Thank you.
Yeah. And thank you again for listening to this interview with Professor Richard Holm from Harvard University, one of the true giants in the area of inorganic chemistry and as a contributor and supporter to the journal Inorganic Chemistry.